All right, so in this scenario, we've got a bat that is on some sort of pivot, and we displace it. Well, it's a terrible bat, but we displace it some angle that's less than 15 degrees, because those are our conditions in order to have simple harmonic motion. When we displace it, we always look at it from the center of mass of the object. And we want to think about, in this scenario, because it's creating a rotation, we want to think about the torque, not the force, but the torque that's being applied to cause it to rotate. So in this scenario, the torque is equal to inertia times alpha. And that torque force has to be perpendicular to the pivot arm, right? And so the perpendicular force would have to be pulling in this direction, but we don't have any actual forces pulling in that direction. So when I break it down, I've got a gravitational force, and it's not really a tension force, but it's the force of the pivot point on the bat. So I could call it force of P, pulling at that angle. And when we break this up into components, let me rotate the axis here. Then we want the component of mass times gravity pulling to the left, because that would be this component right here. So if this is theta, this is mg cos, this is mg sine, and that would be the torque. So let me use a different color. This is our torque. So now in this scenario, we've got mg sine of theta is equal to I alpha. And what I'm going to add to this is that we have inertia from the rotational axis, not just from the shape of the baseball bat, but because we have a pivot at the end, we have to shift it. In this scenario, we're just going to kind of isolate the alpha. So this is where our differential equation comes in. A differential equation is this second derivative that we have here. We have the second derivative of theta with respect to t. And if I divide the RA to the other side, that gives me mg sine theta divided by inertia with respect to the rotational axis. And this is all they want. This is a differential equation. So for part B, it says use the analogy to a mass oscillating on a spring to determine the period of the bat's motion. So this is how we derive the period of any sort of simple harmonic motion. First thing we want to do is take the fact that the differential equation based on simple harmonic motion actually gives us omega squared theta. This is all in rotational form. Originally, when we worked with it in just with springs and masses, we had second derivative of x with respect to t is equal to v squared x, but this time it's all in rotational form. So if I take this equation and relate it to this equation, then I know that I can pull out omega squared from that. The only problem is I don't have theta. And we did learn that because our angle is less than 15 degrees, that sine theta would be about theta. And again, theta would have to be less than 15 degrees. So we can go ahead and make that substitution. My d2 theta over dt squared is equal to mg theta over inertia. And from there, my omega squared is mg inertia. Okay, so we've got omega is equal to the square root of mg over inertia, but we also know that omega is equal to 2 pi over period because that's the distance of one cosine, and it's over the time it takes for one cycle. So then we're going to solve for t, and that would give us our answer. So what I'm going to do first is I'm going to square both sides. So I end up with mg over inertia is equal to 4 pi over t squared. I'm going to bring the t to the other side and then multiply by the reciprocal. And then take the square root. Oh, I forgot. If I'm squaring both sides, I need to square the pi as well. And then when I take the square root, I end up with 2 pi square root of inertia over mg. So in this scenario, we would do the inertia from the rotational axis. And you can compare this to the equation in your notes, and this is how you derive that equation. For part C, it says, describe an experiment that you would perform to measure the moment of inertia of the bat. Include the list of additional materials and write a detailed procedure on how you would obtain them. Well, what's nice is you had a bunch of problems in your FRQs that were experimental designs. And so you can just use those examples to create an experiment. In this scenario, we're solving for inertia, which if I want to solve for this, I want to isolate that from our equation. So the first thing I'm going to do is, let me get rid of that circle, but I'm going to take t over 2 pi, because I'm dividing the 2 pi over, and then I'm going to square both sides. So then I get t squared over 4 pi is equal to inertia over mg. And then I'm going to multiply the mg over. So I get t squared mg all over 4 pi. So from there, I need to figure out what variables I need. I need the period, and I need the mass. Gravity and 4 pi are all constants, so obviously the first thing I'm going to do is to use a scale to measure the mass of the bat. Second, I am going to rotate the bat. I'll call it 10 degrees just to be safe, and time how long it takes to make 10 oscillations, which is, I think there's a double L here, which is what the examples that they gave us in the homework problems. And obviously oscillations are one full cycle, so when it goes to the other side and back to its starting position. And then from there, divide time by 10, plug period and mass into this equation and solve for I. And that would be your experimental design. The last part, D, is asking how to find the center of mass. I'm not going to show it because I don't want to erase the experimental design for part C, But for part D, to find the center of mass of any object, especially if it's a long object like a bat, is to balance it on some sort of pivot. And so a lot of the time I'll do this for my regular physics class, is to balance a broom on my finger. You can use any sort of pivot point, but it's a good way to find the center of mass. So in this scenario, balance the bat on a pivot and find the location where the bat is able to balance. And that would be the center of mass of your object.